We are now going to look at question number 22 of the extra classwork. Please listen to this screencast very carefully, pausing it at suitable points. You can replay it. You can replay certain sections of the screencast if you don't understand them after the first hearing. And when you fully understand it, then you write down the solution of this question in your classwork book as if you have attended an actual lecture. So I'll begin by reading the question. A and B are two towns, and these two towns are separated by a distance of 30 kilometers. So this particular spot over here, let's call it town A, and this is a straight road, and at the other end of this road is this spot over here, which is town B, and the distance separating these two towns is given to be 30 kilometers. Now the question further states that there are cyclists which are traveling from A to B, and the data about the cyclists is a cyclist leaves A for B once every 10 minutes. So this is the time separating the departure of any two successive cyclists, 10 minutes, and the speed of each cyclist is 30 kilometers per hour. Now obviously, if this is the speed of a cyclist, then one cyclist would take 1 hour to complete the journey from A to B. And we are going to now include the cyclists in the diagram which we have just drawn. So there is going to be a procession of cyclists, and we have to now calculate what is the distance separating two consecutive cyclists. You can imagine that there is one cyclist who has just set out from town A. So I'll show him by this cross over here, and the cyclist who had set out earlier prior to him is over here. Now I just want to find out what is this distance. Now the earlier cyclist has been traveling for 10 minutes, which is, of course, 10 minutes is 1/6 of an hour, and he has been traveling, he or she has been traveling for 30 kilometers per hour for 1/6 of an hour. So naturally, the first cyclist, the cyclist who set out earlier, has traveled a distance of 30 kilometers per hour into 1/6 of an hour, and that's going to be 5 kilometers. So I'll put this 5 kilometers in the picture. This distance is going to be 5 kilometers between two successive cyclists. The next cyclist will be ahead of this one by another 5 kilometers, so that cyclist will be somewhere over here, and so on. Now how many cyclists do we show in this picture? So naturally what we can do is we can divide 30 kilometers by 5 kilometers, and the answer turns out to be 6. So there will be 6 stretches or 6 regions or portions of the road, and each portion is 5 kilometers long, and at the end points of each stretch you will find one cyclist. So that's the sort of diagram you will get. All of these red crosses indicate cyclists, and they are traveling from left to right in the picture, and one cyclist, the one at the extreme right, this person has just reached B, and there is a cyclist over here at the extreme left who has just started from A, and there are 1 2 3 4 5 cyclists in between, and there are 5 kilometer stretches of road which separate the cyclists, and if you count these 5 kilometer portions, they are going to be 6. So 1 2 3 4 5 and 6. So that's how we have drawn this particular figure. Now at the moment one cyclist just reaches B, so naturally we are talking about this cyclist who has just reached B, At that same moment, a motor car starts from B. So this is the motor car, and this motor car is traveling towards A, and the speed of the motor car is given to be 30 kilometers per hour. So this is a motor car which travels from B to A at this speed, and naturally the motor car takes 1 hour to complete the journey. And the question is, how many cyclists does this motor car meet on the way? And the phrase "on the way" has to be interpreted to mean that we have to ignore the cyclist or cyclists which the motor car meets at the town B and at the town A. If at all he meets anybody at the town, matlab at the starting point or at the end point of the journey, then those cyclists have to be ignored. It is only those cyclists who he meets on the road which have to be counted. So for example, in this picture, this particular cyclist who is just reaching B at the moment the motor car leaves B, you have to ignore this cyclist. And similarly, it may happen that when the motor car reaches this town A, at that point of time there may be another cyclist who is leaving A. So that cyclist also has to be ignored, and the other cyclists are met on the road or on the way, so they have to be counted. And the question asks, how many such cyclists does the motor car meet? Now at this point of time, I advise you to pause this screencast and just try to figure out the answer yourself. You can give yourself 10 minutes, or if you want a bit more of time, try to figure out the answer yourself, and after you have got some solution, you can start the screencast again. You can continue it and just see whether you have got the right solution or whether you have gone wrong. Now I do consider this question as a slightly difficult question, and the most common mistake which students make is the following. They know that the motor car takes 1 hour to complete the journey, and they also know that there are cyclists which are leaving A for B once every 10 minutes. So if you count this time of 1 hour, you can actually count how many cyclists leave A. So what these people do is, the cyclists leaving A, how many of them leave A in 1 hour? So naturally, if I divide 1 hour by 10 minutes, now 10 minutes is 1/6 of an hour, so you get 6. So there are 6 intervals of 10 minutes in 1 hour, and at the beginning and end of each such interval, a cyclist will be leaving A. So naturally there will be 7 cyclists which leave A for B in 1 hour. For those who don't understand why I added 7, it's like this: at t equal to 0, what are the times involved? T equal to 0 is the time when one cyclist leaves A, and 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, and 60 minutes. So this number 6 is these intervals. There are 6 such intervals. So 1, 2, 3, 4, 5 and 6. There are 6 intervals of 10 minutes in a total time of 60 minutes. But if you count the end points of these intervals, so you have one cyclist leaving at t equal to 0, 1, 2, 3, 4, 5, 6, 7. So I add 1. So 7 cyclists leave A for B, and probably what most people would do is to say that we have to ignore the first cyclist and maybe ignore the last cyclist. So some people would claim that the answer is 5 cyclists. Now people who don't ignore the last and the first cyclist, they would say 7 cyclists, or some people would ignore the first cyclist and you would say 6 cyclists are met on the way. That depends on which cyclist you choose to ignore. Now unfortunately this whole line of reasoning is wrong, because the actual answer, if you ignore the cyclists which are met at A and B, is 11 cyclists. The total is 11 cyclists. Now the mistake in the reasoning which I just discussed, in which you get an answer of 5 or 6 or 7, is the following. You have assumed that when the motor car reaches A, well, we are pretty sure that the motor car takes 1 hour to reach A. Now in this 1 hour you have 7 cyclists who set out from A. That's for sure. So if the motorcycle, let us say, the motor car leaves at, let's put some time, let's say the motor car leaves B, for A, it leaves B at, let us say, 5 p.m. just as an example. Now it's going to reach A at 6 p.m. and from 5 p.m. to 6 p.m. there are 7 cyclists which set out from A going towards B. Now 7 would include the first and the last one. Let's just assume that they are to be counted initially. Now the mistake in the reasoning is you have assumed that the motor car is going to meet only those cyclists who set out 5 p.m. or later, and that is up to 6 p.m. But if you look at the picture, just look at the diagram, the time in the diagram is obviously 5 p.m. That's the time when the motor car has left. And all these cyclists, all of these are cyclists who have left A earlier than 5 p.m. and these are the ones that we have not counted. So naturally the motor car is going to meet more cyclists on the way. In fact, the motor car, if the time in the diagram is 5 p.m. then this particular cyclist must have left A 1 hour ago. That is, he left A at 4 p.m. So naturally you have to add 1 hour to this process. The motor car is going to meet all of the cyclists who leave A from 4 p.m. to 6 p.m. because 6 p.m. is the time when the motor car reaches A. So it's a 2-hour process. It's a process which takes 2 hours. So we ask ourselves, how many cyclists leave A for B in this 2-hour interval? So what I'll have to do is to divide 2 hours by 10 minutes, because that is the time interval separating 2 successive cyclists. So 2 hours divided by 1/6 of an hour, that's 10 minutes. So I get 12. Now there are 12 time intervals of 10 minutes in 2 hours, and at the beginning and at the end of every such 10-minute interval there is a cyclist who is going to leave A. So naturally, by the earlier logic, I must add 1 to this. So I get 13 cyclists leave A for B from 4 p.m. to 6 p.m. Now why is my answer 11? Because the cyclist who leaves at 4 p.m. he reaches B at 5 p.m. In fact, in the picture, the cyclist on the extreme right, that's the cyclist we are talking about, this one. So this one we don't count because he is met by the motor car at the end of the journey. So we have to count only those whom he meets on the way. And similarly, when the motor car reaches town A, the time is going to be 6 p.m. and we know that at 6 p.m. there is going to be another cyclist who leaves A for B. So that cyclist also we have to not count. So I must subtract the first and the last cyclist. So my answer is going to be 11 cyclists are met on the journey, on the way, by the motor car. So this is the first method to solve the problem, and you may have noticed that we have constantly been in the ground frame while solving the problem. There is another method, a very nice method to solve the problem. The same problem can be done in the reference frame of the motor car itself. So in the second method, we have to understand one thing. See, actually what happens is all the cyclists are gathered at the town A before they leave, and every 10 minutes one cyclist is allowed to leave, and naturally some of these 11 of these the motor car meets on the way, and so on and so forth. Now just imagine a situation where instead of all of the cyclists being actually gathered at A, let's assume that there is some town over here, back here, very far away, some town C, and the cyclists are traveling in exactly the same way. That is, they are separated. If you go 5 kilometers back, you will see a cyclist coming towards the right, and this is a procession of cyclists. It's a very long procession. It goes right up till town C. Now listen carefully. We have already seen that our answer is 11 cyclists by one method. If I change the problem in this way, that is, the cyclists are now moving in a slightly different way. They are moving in a procession, of a continuous procession, but they are separated by 5 kilometers. Just as the actual cyclists from A to B are separated by 5 kilometers. And secondly, the whole procession, each cyclist in the procession is still moving at the same constant speed of 30 kilometers per hour. So for example, after 10 minutes, this particular cyclist will actually reach town A, and it will appear as if he has set out from town A, whereas in the actual question this cyclist is at town A for quite some time, and when his time to leave comes, it is at that same time that he starts from A. So I want you to convince yourself that we have not really changed the question in a manner which will change this answer. The number of cyclists which are met by the motor car is not going to change, irrespective of whether they are gathered at point A and they leave one by one, or whether there is a very long procession like the one which I just described. So the number of cyclists met will not change. If you are convinced about that, then we can proceed as follows. Let's solve the problem in the frame of reference of the motorcycle, sorry, of the motor car. So I'll redraw the entire diagram in this particular reference frame, the frame of the motor car. The motor car is now at rest. It's continuously at rest, and you have town B over here, and you have town A over here, and town B and town A, both of them are now moving. So the towns are no longer stationary as viewed by the driver of the motor car. That it is the towns which are traveling at 30 kilometers per hour towards the right. But the towns themselves are not going to be important actually in this particular method. In fact, I'm going to rub them out after some time, but let me right now leave them so that I can draw the cyclists. So this is the time when the motor car is actually leaving B in the ground frame, or we can say B is leaving the motor car, because we are now in the reference frame of the motor car. And naturally this particular cyclist is still going to be, he's going to be over here. All of these cyclists will be in the same positions that they are in the earlier picture. So this cyclist, I'll have to draw him over here, and the next one, and then the next one, and so on. So let's see, there should be 7. 1 2 3 4 5 6 7. So that seems okay. And we draw the other ones now, because it's a procession of cyclists. So there are so many cyclists which are just going towards the right. All of them are going towards the right. It's a long procession of cyclists, and each cyclist is traveling now not at 30 kilometers per hour, but remember, in the ground frame the motor car was going at 30 towards the left, 30 kilometers per hour towards the left. The cyclists were traveling at 30 kilometers hour towards the right. So naturally, as viewed by the driver of the motor car, the cyclists and the procession, the whole procession of cyclists is moving at 60 kilometers per hour towards the right. And because distances are absolute in classical mechanics, the distance separating any two consecutive cyclists is still going to be 5 kilometers. That doesn't change. So you have to imagine this long procession of cyclists moving towards the right, and imagine the driver of the motor car. So he feels that he himself is stationary, and he's looking out of the window, and he's seeing these cyclists move towards the right, one after the other, and he is observing the procession for a total time of 1 hour. We know that as far as the motor car driver is concerned, if I borrow the times from the previous method, the process begins at 5 p.m. and ends at 6 p.m. That is, he leaves B at 5 p.m. and reaches A at 6 p.m. Or in his reference frame, the town B is with him, is near him, or is by the side of him at 5 p.m. and at 6 p.m. town A has come there. So this whole process takes 1 hour from the viewpoint of the motor car driver, and in this 1 hour a procession of 60 kilometers moving at 60 kilometers per hour is moving past him. So naturally a 60 kilometer length of the procession moves past the window of the motor car, the driver, in this time of 1. So we just have to count how many cyclists are there in a 60 kilometer length of the procession, and we know that this is 5 kilometers. So how many such segments are there? So 60 kilometers, when I divide it by 5 kilometers, I get 12 segments. There are 12 segments, each of 5 kilometers, and these segments constitute the 60 kilometer length of the procession, which the motor car driver sees through his window. And since there are 12 segments, and at the end point of every segment, the beginning and the end, there is one cyclist, so naturally I must add 1, and I get 13 cyclists. So there are 13 cyclists, and there are 12 5-kilometer segments totally in between them. So the car, or the driver of the car, sees 13 cyclists, and naturally one cyclist is seen at t equal to 0, or what we have said at 5 p.m. and the last cyclist, the 13th cyclist, is seen at t equal to 1 hour, or what we have called 6 p.m. in our previous solution. So let's neglect, or let's ignore the first cyclist and the last cyclist, because the first cyclist, when the first cyclist passes the motor car driver, the motor car is at point A, or point A, the town A is with the motor car, sorry, it's B, sorry, town B is at the with the motor car. And likewise, when the motor car meets the 13th cyclist at 6 p.m., the motor car is at the town A. So we have to neglect those two. So 13 minus 2, and I get 11 cyclists. So by this method of relative motion, we can get the same answer, that is, the motor car meets 11 cyclists on the way. Now if you have understood whatever has been presented, then you please write it down in your notebook, and in my next lecture I will start after this question. I will start at a point where it's after this question. If you have not understood it, you go through it again and again and try to follow, and finally once you do that, you can write it in your notebook.